All right, we're going to finish up last section that we're doing in chapter 5, which is 5.5, and that's on logarithms, and specifically solving. We'll do a little bit of solving. We're going to be graphing them. Some graphs we'll do by hand, some we'll do on the calculator. Transformations is something else we'll look at, like the shifting, the stretching, all that stuff that we've done before. Now, if we have to graph something on the calculator that's not base 10 or base E, remember, we don't have a button for it. So we have to use the change of base formula. This is something we talked about in section 5.4. But when you don't have a base 10 or a base E, the way you can type it in is as a fraction. And the fraction is the log of the argument divided by the log of the base. And you do have to remember which one goes on top. And the way I always remember it is the base. I think of the base of something is usually, it's at the bottom of it, like the base of the building. It's at the bottom of the building. So the base, that log always goes in the bottom. And the argument, that log always goes in the top. Right, so if we had something like log base 3 of 15. That's basically saying 3 to what power would give you 15 if you rewrote it in exponential form. Well, let's get an estimate of what it's between. 3 to what power gives you 15? The power is going to be between what two numbers? Yeah?
2 and 3.
It's going to be between 2 and 3, because 3 to the second is 9, 3 to the third is 27. That's too big. So it's somewhere between 2 and 3. To figure out exactly what it is, that's what we would type in on the calculator. Remember, when you type it in, the calculator is going to add a parenthesis. You need to close it when you are done with the 15. If you don't close it before doing the division, it will not come out right. The last one, technically, you don't have to close it because there's nothing else coming after it. But we just said it would be between 2 and 3, and that's what it is. Now, you can type it in using logs, or you can type it in using ln. It will come out exactly the same. Don't mix log and ln, though. Either use both logs or use both ln's. Okay. Any question on that? So let's find a graph, and then we'll look at the domain and range of this. All right. So I want to type that in because they're asking me for a complete graph, but I don't have a button for base 3. Can someone remind me, how will I rewrite that so I can type that in on the calculator? Yep, Lens.
Would it be log 3 over log x?
Okay, and we got to remember which one goes in the top.
The log x.
Log x. Yeah. Remember, 3 is in the bottom, so that stays in the bottom. All right. Now, another way you could think of that, kind of like if you had a fraction like, let's say you had x divided by 3. If you wanted to write that as multiplication, what's x divided by 3 the same as? Raj? Right, it's the same as just doing 1/3 x. That's x divided by 3. So that's basically what you have right there. This isn't 1/3, this is 1 over log 3. It's 1 over log 3 times x. The reason I wrote it that way is because I want you to recognize that as a transformation. when you multiply by a number in front, oops, don't forget your log x. What kind of transformation is it when you multiply by a number in front? Yep.
Vertical stretch.
That's a vertical stretch. So technically what we're doing here is a vertical stretch of the log function. 1 over log 3 is going to end up being a decimal, so it's actually going to shrink. But it is a vertical stretch of log x. All right, let's graph it and then see if we can get the domain and the range. Okay, I'm going to type it in as the fraction log x over log 3. If you want to do the 1 over log 3 times log x, take it out. So log x and divide by log 3. All right, let's start with zoom 6 and let's see what it gives us. So is that a good sketch? That's what the calculator gave me. Is that a good sketch? Oh, Jaden, what do you think?
Yeah.
How come?
I don't remember why.
All right. So anybody else tell me either why you agree with Jaden that that is a good sketch, or if you don't, tell me why it isn't. Yeah?
I think I agree because it shows the starting point of the graph and it shows the end game, which is going like as x increases, the function increases as well.
Okay. So we can definitely see there's the behavior going to the right. It's gonna, looks like it levels off, but it never does. It does keep going up and to the right. We graphed log functions when we did exponentials the first day, and I showed you that they were reflections over the line y equals x. So we've seen what a log should look like. That is not what a log should look like. What's wrong with that picture? Yeah?
Like it has like a stopping point at the bottom, and it should just keep going down the y-axis.
Right. It should just keep going down. It looks like it almost looks like it has a starting point, right? Kind of like a square root function or something like that. That's not what it should look like at all. And if I zoom in, right, zoom 2, right now it looks like it's, at least to me, it looks like it's starting at -2. If I zoom in, let's see what happens. Now it definitely looks like it's going below -2. Now it looks like it's at -3. Why is the calculator having such a hard time drawing this? Yeah?
Because it's too steep going down for the calculator to display it.
Yeah, it's getting almost vertical. Remember, exponential functions have horizontal asymptotes. These are the inverse, so they have vertical. So that, if you look at that sketch, it is misleading. Okay, that is not what a log function should look like. It should keep going down like that. And it does keep going to the right. I think that part was fine. Okay. So now, let's see if we can describe the domain. Nick, what's the domain here?
X is greater than 0.
Right. It's every value greater than 0, because there's a vertical asymptote at 0. And what about the range? What's the range? Dario, what's the range here?
These are all the numbers.
All real numbers. Yeah, the graph is going to go down forever, and it does go up forever. It goes up extremely slow, because it's a log function, but it does go up forever. And as far as finding a complete graph, I would say the standard window is fine. That's as good of a window as you're going to get. But keep in mind, it doesn't really show the vertical asymptote the way it should. Okay. So any questions on that? So with that last problem, I kind of started to get into what we're going to do right here, which is transformations. Okay, so I'll label them. I know sometimes we skip the labeling and I do it verbally. We got a little bit of extra time, so I'll label them. I'm not going to put all the details in, but I'll label some of what you need to know, and the rest of it we'll talk about. So let's start with A. A could be addition or subtraction inside the log function. So when I say inside the function today, I mean inside the argument. What does A do? Causes the graph to?
Horizontal shift.
Yep, horizontal shift. And if you add, that would shift your graph to the left. And if you subtract, to the right. Okay, so you do need to know that. I'm not going to write that part down, but that is important. Okay, B, still inside the argument to the log function, but now it's multiplying x by a value. It's not adding or subtracting. So what kind of transformation is B? Yep.
Horizontal stretch.
That's a horizontal stretch. If B was 2, how would you describe the stretch? If B was 2. Remember, it's horizontal.
It would be a horizontal stretch by a factor of 1/2.
Yep, horizontal stretch by 1/2. So the bigger you make B, the more compressed the graph gets. If you make B very small, like 1/7, then it would stretch it by 7 times as much. Now, what if B is a negative number? That's the third thing that can happen inside the argument.
Is
Yep.
that a reflection?
That's a reflection. Which axis does it reflect over? Yep.
The Y.
The Y. Okay? So you have to remember, when you do a horizontal reflection, that means you are flipping left to right. That's a horizontal reflection. That's over the y-axis. Okay, so that's the 3 transformations that A and B can cause, and you always do them in the order indicated by the letters. Horizontal stretch, horizontal shift, horizontal stretch, horizontal reflection. Those are your first 3. Okay, and now the last 3. Okay, C. Now we're on the outside of the function, outside the argument, and we are multiplying. Just saw an example of that in the last question. What does C do? Rush? Yep, it's a vertical stretch. Okay, so vertical stretch. What if C was 5? How would you describe what's going to happen to the graph? Yes?
Vertical stretch by a factor of 5.
Yep, nothing backwards about it. Vertical stretch by a factor of 5. If C is a half, it's vertical stretch by a half, which really compresses it. Now, what if C is negative? What does that cause the graph to do? Yep.
Reflection of the x-axis.
That's a reflection over the x-axis. So that's a vertical reflection. Think of it like that. It flips up to down. Yep. All right, and our last transformation is D. It's like A. It's adding or subtracting, but now it's on the outside. So what does D do to the graph? Let's.
Be a vertical shift.
Yep, that's your vertical shift. And a positive would shift the graph for D. Positive would shift it up. Yep, and a negative would shift it down. So the 3 transformations you handle for the verticals are in the following order, and they're always after the horizontal. First you do vertical stretch, then you do the vertical reflection, then you do the vertical shift. So there's a total of 6 possible transformations. Just like every function we've done all year. There's no difference. Okay. Any questions on transformations of logs before we do an example? Okay, so it says, how can log base 3 of negative x be graphed from log base 3 of x? Well, first thing is when you are comparing two logs, they need to have the same base. If they didn't have the same base, that would be like me asking you to compare a square root to a cube root. They're different. You can't compare them. So whenever you're transforming logs and comparing them, the bases will always be the same. All right, so first of all, how many transformations are there to change what's circled in blue into what's circled in red? Yep,
One.
just one. Yep, there's only one transformation. All right, so let's write this down. So to graph y equals log base 3 of negative x. Can anyone tell me what is the one transformation that you would have to do? Yep, Travis.
Flip over the y-axis.
Yeah, so to graph y equals log base 3 of negative x, reflect the original over the y-axis. Horizontal, yeah, over the y-axis. Okay, we'll do another one in a minute where we have to describe more transformations, but that's the only one in this one. Now they want to know the domain, the range, and the vertical asymptotes. Well, if you think back to the one that we just did, even though this has a vertical stretch with it, or in this case actually vertical compression, it didn't affect the domain. Stretching something up and down never affects the domain. So that is the domain of log base 3 of x. If you reflect that, what would be the domain of log base 3 negative x? Yep.
X is less than 0.
Yep, x is less than 0. Okay, so that's the domain. How about the range? If you reflect it horizontally, what would the range be?
Still be all real numbers.
It'd still be all real numbers. When you graph a logarithm, the range never changes. Range is always all real numbers. Just like when you do an exponential, the domain is always all real numbers. And it's because they're inverses of each other. And I thought there was one more thing they wanted. Vertical asymptote. What would be the equation of the vertical asymptote if you reflect that graph over the y-axis? Yep.
X equals 0.
It's still x equals 0. Yep. Okay, any question on that? All right, let's try this one. Log base 10, there's no base, of 3 minus x. That's the new graph, and we're sketching that from the graph of log x. Okay. How many transformations does, you know what, actually let's just add something in there too. I added times 4 in front. Okay. How many transformations does this one have now? 3. Yep, there's 3 transformations. Okay. What would you can rewrite the argument if you want it to match the template that I gave you there. You don't have to, as long as you can just tell me the 3 transformations in the correct order. What would be your first transformation here? Raj?
Horizontal shift left.
Yep, so we're going to shift left 3 units. Okay, my second transformation would be reflection over the y-axis. And what about my third transformation? Yep.
Vertical stretch 4.
Vertical stretch by factor of 4. All right, now let's say I do want to figure out the vertical asymptote. Where's the vertical asymptote if you don't do anything to it? No transformations. Yeah?
0.
It's at 0. The only thing that would ever affect the vertical asymptote is what's inside the parentheses. If you take a vertical asymptote and you stretch it taller, well, it already went up and down forever, so stretching it up and down doesn't make a difference. And if something goes up and down forever and you shift it up or down, that doesn't make a difference either. So focus on the 3 minus x. And anybody think they could tell me where the new vertical asymptote would be? Yep. No, it wouldn't be at -3. I mean, I do see why you got that though. You got to be careful. Yep.
3.
It would be at 3. So think about, like, just imagine a single point on the vertical asymptote. The vertical asymptote is starting at 0. The first thing that happens to the vertical asymptote is it gets shifted 3 units to the left. So it ends up over here. Then every point gets reflected over the y-axis. So it ends up back over there. Okay, so this would have a vertical asymptote at 3. And if you want kind of a way where you can figure that out, where you don't have to really think about the number line like I just did, if you take the argument and set it equal to 0 and solve it, that number that you get will be the new vertical asymptote. So subtract 3 from each side, and then divide by each side by -1. That's how you can always figure out the vertical asymptote. Just set the argument equal to 0, and it'll give it to you. Yes? Okay. Any question on that one? All right, so now let's take a look at sketching a log. So when we're sketching logs, the nice thing about a log is, first of all, it only goes in one direction. So we don't have to worry about sketching points forever in both directions. But you do have to find the vertical asymptote. I was going to tell you how to do that in a minute anyway. So when you set the argument equal to 0 and solve it, that's your vertical asymptote. X and y-intercept, well, y-intercept you can always find, because remember the range is all real numbers. Sorry, x-intercept you can always find, because the graph goes up and down forever. So logarithm functions will always cross the x-axis, but they might not cross the y. An example of one that doesn't, right there. Okay. If your vertical asymptote is the y-axis, then you'll never cross the y-axis. Right. So when I suggest finding the y-intercept here, well, we can try, but if it doesn't work, then that's not helpful. Okay, but x-intercept, yep, vertical asymptote, always. So just a reminder of how you find your intercepts. So you find the x-intercept, that's when you plug in 0 for y. To find the y-intercept, that's when you plug in 0 for x. Now, it seems like it's backwards, but that's how it works. If you need some more points, which you probably will, we're going to use the table on the calculator, and that'll help us get a few more points. Remember though, you have to make sure whatever you take the log of is a positive number. If you try to take the log of a negative, what's going to happen? Remember what happens when you try to take the log of a negative? Yeah?
Like imaginary.
Right, it comes out imaginary. Okay, so it's not that you can't do it, it's just that for graphing, that's not going to help. Okay, and you can pick any x's you want. Doesn't as long as the argument comes out positive. I generally try to pick x's that are going to fit on the graph I'm trying, the graph paper. All right, so let's try this one. So we're going to sketch a complete graph of log base 2 of 3x plus 5. Okay, so first thing that we'll do is find one of the things I mentioned up above, either the x-intercept, the y-intercept, or the vertical asymptote. Lens, which one do you want to try to find first?
Maybe the vertical asymptote.
Vertical asymptote, okay. So let's start with that. Can you tell me the equation that I would need to set up and then solve to get the vertical asymptote?
3x plus 5 equals 0.
Yep. 3x plus 5 equals 0. There we go. And I'm going to graph that right now. Negative 5/3. What is negative 5/3 as a decimal? That way when I graph it, it's easier to think about. Yeah.
It would be like -1.33 something.
Negative 1 point what?
1.33.
That'd be negative 1 1/3. That'd be negative 4/3. Negative 1.3 repeating. This is negative 1.6 repeating, so negative 1 2/3. Okay, so let's graph that. Okay, so vertical asymptote at negative 1 2/3. Okay, so negative 1 2/3, right about there. All right, now they want us to find, let's do the intercepts. Okay. Let's start with the x-intercept. That's when you plug in 0 for y. So g of x, and then solve. So we've got 0 equals log base 2 of 3x plus 5. So that's an equation in log form. How are we going to solve it? Yeah?
Log of 3x plus 5 over log of 2.
Okay, so we could split that up into a fraction, but then we still have to deal with getting the variable by itself.
So divide by log of base 2.
You can't divide, so remember, you can't divide by a function name. You can only divide by variables or numbers. So what else can we do with that? It's one of the first things we learned how to do with a log equation. Yeah? Yeah, let's just make it exponential. If you make it exponential, what would your base be? Yep, the base would be 2. What about the exponent? Nope, that's the argument. So remember, when you argue with somebody, you end up alone. 0. Logarithm always equals the exponent. And the argument ends up by itself. So now we have a very simple equation to solve for x. So we get 1 equals 3 to the x plus 5. Bring your 5 over. And divide by 3. So your x-intercept is at negative 1.3 repeated. Right about there. Okay. Let's find the y-intercept. That's when we plug in 0 for x. So log base 2 of 3 times 0 plus 5. Okay, now we can do what Evan, I think it was Evan, you said earlier, use the change of base formula. That's going to be log of the argument, which is 0 plus 5, divided by log of the base. That is your y-intercept. Log 5 divided by log 2. Okay, so we got a y-intercept of 2.32. So for graphing purposes, a little bit above 2. Right there. All right, so we've got 2 points, but we're going to need a few more points. What can we do to quickly get some more points without having to keep plugging numbers in by hand? Travis?
We can only calculate it and go into a table.
Yeah, let's just use the table. All right, so let's put in log of 3x plus 5 divided by log 2. Okay, so we can go to the table. We can check when we plug in 0, make sure we did that right. 2.32, that's what we got. Notice if you try to plug in negative numbers for x, that's a problem because it makes the argument negative and we get an error. So we have to pick numbers that are to the right of the asymptote. All right. What would be a good value to pick that's to the right of my asymptote? Layla, what would be a good value?
1.
Okay, we could do 1. Kind of close to 0, so we're not going to get a ton of information about how that curve is going to look, but it does give us 1 more point right there. Okay, how about Dario, another good value?
4.
Okay, so yeah, we want to kind of space it out a little bit. So 4, we'll call it 4, 4, roughly. And maybe 1 more value. Yeah? 7. Yeah, I'm just going to go all the way to 10, just so I get a point right on the edge of my graph. 7 would be okay, too. So 7 or 10, a little above 5. Okay. So now I've got a good idea of what the curve is going to look like. Remember, the closer you get to that asymptote, the more of a vertical asymptote, the more the graph drops down. So it's extremely vertical. So the calculator is not going to do a good job at all with graphing that. It's going to look like it has a start point. So if I ask you for a sketch of a logarithmic function, and you sketch something that has a point where it looks like it starts, it's not right. Okay, it should drop down further. All right, so that's the sketch. We've got the asymptotes. We've got the intercepts. We have not done the domain and the range. Okay. What is the domain here? Yep.
X is greater than negative 5/3.
Yep. Anything greater than negative 5/3. And what will the range be? Yep. All real numbers. Yep. There you go. All right. So any question on finding domain, range, asymptotes, or making a sketch? The last question. So the last question we're going to look at is an application of logarithm. And it's a formula that's used to measure the intensity of an earthquake. Okay, so if you've heard of the Richter scale before, that's the formula that our book gives us for it. So the R is the intensity of the earthquake. That's the number that you hear about when you hear about an earthquake, like on the news. Right? They'll tell you like it's a magnitude 4.7 earthquake. That's R. There's three values that go into calculating R. The first one is A. And A stands for the amplitude of the vertical ground motion measured in micrometers. So if you think of, imagine dropping like a rock in the middle of a pond. You see waves come out. It's exactly what happens in an earthquake, except the waves aren't going through water. Well, they can. But a lot of times they're going through land. And that's why it causes lots of problems with buildings, because the ground is flexing like a wave. And if the building's not designed to handle that movement, then it would have some damage. Okay, so A is the amplitude of the vertical ground motion. T is what we call the period of the earthquake wave. So let's say, kind of like an example, you were standing at the beach and you were counting how many seconds between each wave coming in. Okay, this isn't exactly the period, but it's pretty good metaphor. If you count how many seconds it takes between the waves coming in, that's called the period. It's how often a wave is hitting you, basically. And the last thing that they use in the formula is B. And B is a factor that accounts for the weakening of the wave. It makes a big difference if you take a rock and you drop it in a pile of sand. You'll get a crater around it. You'll see the wave come out. Or if you drop it in water. The sand is loose, so it kind of absorbs the energy. And remember, the Richter scale is a logarithmic scale, kind of like if you remember pH in chemistry. When you go up by 1, it's really going up by a factor of 10. So a Richter scale, let's say your earthquake was a 3 versus a 4. The 4 is 10 times as powerful. If you had an earthquake magnitude 5 and then an earthquake magnitude 3, the magnitude 5 is 100 times the magnitude. Yeah, the magnitude 5 is 100 times the intensity. So just going up 1 makes a big difference when your scale is logarithmic. Okay. So we've got a problem where they're telling us that at the early stage of an earthquake, the amplitude of the ground motion was A, and then later on, it became 10A. I want to figure out what is the difference in the intensity. What is the difference in the intensity of the earthquake if the ground motion increases by a factor of 10? Everything else is going to stay the same. So it's like we're measuring this earthquake at 2 different points. We're going to measure it at the beginning stage. We're going to measure it at the later stage. B is the same at the early stage and the later stage. T is the same at the early stage and the later stage. Only thing that's going to change between the 2 measurements that we take is A. It increases by a factor of 10. And we want to figure out the effect that that has on R, which is called the intensity or the magnitude. Okay, so we're looking at how much something is changing. What arithmetic operation do you use when you're trying to figure out change? Well, Annalise, what do you think? Right, we're going to use subtraction. And we know that later on, the ground motion is 10 times as much. So because I want to get a positive change, it's kind of like if I wanted to figure out the change in the temperature between 3 a.m. this morning and now. If I wanted to get a positive change, assuming it's been warming up since 3 a.m., I would do the temperature now minus the temperature earlier. So that's how I'm going to set this up. So we're going to find the intensity now minus the intensity earlier. So we've got to set up a formula for each one of those. Let's start with the intensity now. Okay, that's when this is like the later stage, and this is the earlier stage. Think of it like that. Okay, so our formula is log A over T plus B. What are we using for the A value at the later stage? How are they measuring the ground movement in micrometers at the later stage? Yeah? 10A. So log 10A over, and then everything else is going to be the same between the 2 measurements, the T and the B. Okay, so that's the calculation for the intensity at the later stage. And what was the vertical ground motion at the earlier stage? How did they say to represent that? Marin, what was the intensity at the earlier stage? A, yeah, just A. So log A over T plus B. So we have to figure out what that simplifies to, and whatever we get, that is the change in the intensity. What could I do first here? see anything, or let's, yep.
Could you just bring the negative sign to the log?
Yeah, well, when you distribute, so yeah, distribute the negative. What would you get when you distribute it?
Just log 10a over t plus 1 minus log a over t.
Minus log a over t, yep,
And with a minus b.
with a minus b. Okay. Now, what's going to happen there? Yeah. Right. Any factor that's staying the same between two measurements shouldn't have an effect on the final answer because it was the same before as it is later, so it shouldn't matter. And that shows that b does not matter. So now we have log 10a over t minus log a over t. All right. Now, let's take each log and break them up. How can we split the first log into two logs? Yep. Yep. Can you tell me what you would be subtracting? Log 10a. Yep. Minus log t. Okay, so there's your first one. And can you do the same thing for the second one? Log a minus log t. All right. So we split each log into a difference of logs. And remember, when you split this second one, you're splitting it into two, but there was a minus sign in front. So that minus sign applies to both. Okay. What could I do at this step? Yeah?
Distribute the negative.
Yep, distribute the negative again. So now we have log 10a minus log t, and what do I get when I distribute the negative, Jackson?
Negative and minus log a plus log t.
Plus log t. Perfect. Okay. Now what's going to happen there?
Log t's cancel out.
Right, log t's are going to cancel out, which again, because the period of the wave was the same earlier and later, it shouldn't affect anything in the answer, and it doesn't. It's gone. Now we have log 10a minus log a. What could we do with that now? Yeah.
Like put it into one log.
Yeah, let's combine it back together. When you combine it back into one log, what would you have?
Log 10a over a.
Perfect. Log 10a over a. All right. And what's going to happen there? Yep, Marcel.
The a's cancel out.
A's cancel out. And now we're left with the log of 10. What's the log of 10? Yeah.
1.
1. There you go. So that means if the vertical ground motion increases by a factor of 10, that's an increase of 1 on the Richter scale. And that's exactly how the Richter scale works, because it's logarithmic. So that problem kind of combines some properties that we did last week, splitting logs, combining logs, and then when you do the distributive property with the negative, a lot of your variables cancel out. Okay, any question on that? If you had done it in the reverse order, you would have ended up with, I think you would have ended up with log 1/10 if you switch the order, and the log of 1/10 is -1. So you would have gotten the same thing, you would have just been looking at it from a different perspective. Change now versus later, or later versus now, kind of thing. All right. So we've already done the 293. So the homework tonight is just 301. Okay, and you've got just about a little over 20 minutes. Okay, so please try to use the time to get a little bit of that done. And if you do have any questions as you work on it, just let me know.